The challenge of systematics is not well or precisely defined at this stage. I'll come back later. So I don't think many of these are part of my personal view as well, so feel free to comment, jump in if you don't agree. Many of these they don't have an exact or correct right answer, but rather always a better assessment, better estimations. And as experimentalists, many of you probably are spending lots of efforts on this. I think as a new student, I was also trying to let you know that it's probably excited if you see a result out as a glance. I tell you that's just like 10% of the work probably. You need to spend at least rest 90% of the effort to investigate systematics, what the results are. So any comments, I would appreciate very much if you come up with any better idea on evaluating systematics. That's actually very great. And I would encourage actually the junior representative can give awards into that. Oops. So talking about systematics, what the definition of this? You probably heard about the word systematic errors, systematic effects, systematic uncertainties. I want to show a slide from Professor Roger Barlow. I think many of you heard about this famous name. This is the slide he showed, and he wants to distinguish. Typically, if you search or Google online the systematic error, this is about definition from the old days of IC that they describe as a reproducible inaccuracy introduced by this faulty equipment calibrating technique. This is in the Beventy's textbook as well, in the reduction data analysis and statistics. While nowadays, Aurier, this is also a particle physicist, in his textbook, it describes the systematic effects as a general category which includes effects such as background, scattering efficiency, energy resolution variations, counter efficiency, with beam position energy, dead time set, and uncertainty. In the estimation, such a systematic effect is called systematic error. So Barrow claimed that, this is the two contradictory definitions, while I think in the nowadays understanding, and he claimed this Aurier is more correct with our understanding, while Beventy is wrong. But what I want to, my take actually is probably saying the Beventy is wrong is not, it's probably a little bit too extreme. My take is that this is, as mentioned, is a kind of old traditional definition of error, while systematic uncertainty is a kind of a estimation or estimate that we want to address how our experimental measurement is deviated from the true value. So first of all, systematic uncertainty is not an error or mistake. If you have any error mistake, that's definitely, we shouldn't count it as systematic error. You have to correct it, fix it. And while in many of our publications or papers, these two terms, systematic error or systematic uncertainty, I see as most interchangeable. It's basically meaning the same thing, I think, nowadays. And the systematics, what we are dealing with actually, this is the uncertainties, what I call it unknown from the uncertainties from the unknowns. If we know any effects or the dependence of any quantity versus another quantity, you should try to correct it. And systematics are not about this kind of correction, and it's probably the uncertainty of correction. So those correction uncertainties are unknowns. So that's also the challenging part, why the systematic is difficult. So the main, I think this is to give you an idea of the typical sources of the systematic errors. They come from many aspects. This is just no particularly order of the category. I'll give you an example in the next slide where you want to think about. So it comes from like imperfect understanding of the experiment. That's probably if not the general understanding, like the tracking efficiency, the energy resolution, skills, etc. The impact, the modeling simulations, like you use a simulator to simulate the detector responses. That certainly comes with some uncertainties. Uncertainty associated with any corrections. You do the experiment to measure your yield in the fixed acceptance, and you need to correct to the full acceptance, to the extrapolation that involves certain uncertainties. Correcting with some other parameters involved, but those are typically like the external parameters. That's rather straightforward to take into account. Theoretical uncertainties. If we do an IA calculation using a binary or any other calculating participant, that comes from uncertainty from the model, and the global model we described weaker. So statistical uncertainty typically, I mean, that's natural, scale by 1 over square brain, not to fancy, but systematic uncertainty, they typically do not necessarily depend on statistics. But however, the more statistics, they'll be helpful because in the sense that they can help you check a lot of systematics, which I'll mention that later on, how to think about it. Therefore, the more statistics would be helpful in some sense to help you reduce the systematic uncertainties. So I'll give you a start with just one example to help you maybe think about where to, how do you want to evaluate the systematics. This is the first thing is really you want to review all your experiment and analysis procedures. The example is trying to say, do we measure the charge pion dn dy in the central go-go collisions? What do we do? So first, certainly, you think about another step. You go connect to the event sample. The central, you select central go-go events, like with vertex centrality selection. You pick up your charge particle tracks. That's actually experiment, the tracking, typically a TPC, reconstruct charge particles with standard anti-HPCA cards that they recommend by staff. And then do particle identification to select your pions with either DDX time flight, and extract the raw yield beam by beam, and then do the efficiency correction, rely on embedding or any other method. If you have a momentum distortion due to the energy loss, that's need to be also corrected for, and also some final resolution correction you need to think about, and then calculate the PT spectrum and do the extrapolation to get the PT integrated if you want. So that's just a simple example. I may be a little bit simplified, but this to get you through. So to think about systematics, I would recommend everyone to think about all your procedure, to think step by step, what kind of effect that could come in to affect your results. For example, let's do step by step. Event selection. Certainly you need to think about what kind of background events you may suffer. In this case, like pileup or whatever other non-go-go collision in your analysis. How do we remove them? Those are, or how do we reject them? Centrality bias in your centrality selection. How do you should be sure to say top 5% and what is the systematic associated? Every step also counts. Charge track selection. When you reconstruct charge particle with this typical standard cuts, so you need to consider what other typical background tracks can come in. Not a real. You want to select the charge pion from the real go-go collisions. So you may have, as an experimentalist, you may select some tracks, not a real track. It's a background coming from the reconstruction, or it's a background coming from the secondary decays. So those are the effects I need to think. Do the particle identification, certainly, the purity, efficiency, PID efficiency that comes in. When you do the raw yield extraction and standard procedure, you do probably a Gaussian assumption to do multi-Gaussian fit to extract yield. So this is a model employed here. What is uncertainty associated with that? Well, what this function form? Is there any systematic associated with that? And when you do the extraction, there's also technical part, what the fit range you use to do that, etc. So efficiency correction, this is a standard embedding, but one also needs to see what's our efficiency uncertainty. This is probably one of the also systematics that affect our spectral results most, and how do we address that? There's a big task force now trying to assess this tracking sufficient uncertainty. This momentum or energy loss correction, and there's probably, because as experimentalists, we measure the momentum from TPC, whether it's the right momentum, if there's any finite correction, you want to think about that and check your simulation in your embedding correction. And when you calculate the spectrum, PT beam by PT beam, and there's probably some finite beam width in your calculation. What is the impact of that? And then to do the extrapolation, certainly the unknown yield, to extrapolate to the unmeasured region. That's obviously also some uncertainty associated. So you can see also you get an overwhelming list of all this associated systematics. So I think it's worthwhile to think just as a whole, the list, and then you may come up with some of this may not be a big effect to your final results, some maybe, but it's worthwhile to think over, and then later on, certainly you want to focus on several leading systematics, try to tack that down first. while some of them are negligible contribution, you may put it aside first. So those systematics actually, if we want to maybe evaluate this one, I think the ways you can think about how to do this, I put this into several different a little bit categories. Some of these are depend on, you can say, a kind of uncertainty as a collaboration as a whole. Some of the uncertainty are studied or learned from previous experience, like the tracking efficiency uncertainty, the energy loss corrections. So many of these that probably depend on a calibration sample or some other independent measures to tell you what is uncertainty associated with this. So I call this use some independent measure or calibration measures to assess this. I'll come to this later on. Many of these are associated with, you try different methods. That's probably standard, not standard, very common way that to evaluate systematics. You choose different weight functions, you choose different models to extract your yield, to extract your corrections. Type variation, that's also a very common exercise to study one effect to this. I associated with these numbers, so this, I'll come to this in details, how do we do that. And after all this, actually, there's also one thing that because we're collecting data, or they come over a long period, typically, and they also span a large range in terms of, events span large range in terms of distribution in your detector, the VZ distributions, your numerosity dependencies, your magnetic field dependencies. Those also always need to check your results stability across all these things and how that will affect the results. So I'll talk about from bottom up first to check the stability. And this is the kind of now, I think, a very good exercise in start the QA procedure become very standard. And to identify any potential impact of the operation that can affect the results. So when you look at all your QA plots, right, this is although this packages actually can deliver such a plot, but you may want to take a look to understand how or to study a little bit how this will affect the results. This is a recent presentation from Mohammed Ibrahim, if I pronounce his name correctly, from 9.2 GeV Go QA shows it's just average 5, the mean 5 event as a function of around IB. You can see a clear step, the change, which could indicate, something you want to know the detail associated with the, you check the wrong log to see whether it's associated with any TPC RDO mask. That's a pretty standard. And then such a step will tell you you want to be a little bit careful if you want to study your results to see whether that your results has any impact across this. So this is runtime and to check result stability. It's a very Euro exercise if you just you split your data sets into 2 periods to see whether the results are consistent. I take this example. The vertex Z position, this is also a pretty standard exercise. The reason is also all our TPC, have finite acceptance, and also calibration has some there's some precision in terms of uniformity and versus position and angle. Your efficiency correction also has this dependence. It's always worthwhile to check your results versus vertex Z. That's I don't see this being exercised very often, but I believe if you want to do precision measurement, that's certainly very important to check. Luminosity, this is particularly associated with if you suffer from some finite pileup, either events or pileup tracks, you definitely want to check your results whether it's stable across the luminosity. Because the potential pileup that will easily leak into your analysis and create, you can say, I think now it's not just a systematic error. This will be a really mistake or error you will need to correct. Magnetic field, because of magnetic field, this is a particular associated with probably the TPC detect calibration, how it's associated with it. And checking, if it's available, checking the results across different magnetic field settings will be also very important. So the common exercise is just split our data sets into different subsets, like different VZE locations, different luminosity regions, different magnetic field configurations, repeat your analysis and check the consistency. If you identify any dependencies, I think this is certainly not critical because I don't, unless you have other reasons, your results shouldn't depend on any of these operation conditions. And you need to probably investigate more whether, I would say this is, wouldn't in the first part to consider just as a systematic error. Try to check your calibration corrections, whether you can fix this or correct this. If you find in the end couldn't find any reason that account for this, probably adding to systematic is just only the last choice that you will say we exhaust all the methods that we couldn't find a reason. But I wouldn't recommend that in the beginning. You want to spend more efforts to repeat, to identify. So the common exercise for checking systematic is trying to vary the cut selections. This is probably I can easily get a question that what cut I need to, the cut say DCA, how do I vary to get an estimation on systematic errors? It's a very challenging question to answer. I don't think I have an exact answer to you, but my suggestion would be any cut associated with this analysis, you want to understand or first know what is a real systematic effect you want to investigate by variance cut. The example here is like typical DCA cut. One of the main purpose of putting DCA, select DCA, is select primary tracks, right? Your DCA less than 3, that's a standard TPC, primary track selection. And the primary selection is trying to avoid any secondary track contribution that leak into your primary selection. So vary the DCA cut, you know what kind of systematic effect you want to study. Then you want to think about, okay, the amount of change, you want this to be not too small, so or not to be large. At least I would say reasonable. I put also quotation mark. It's reasonable is also not precisely defined. How reasonable is reasonable? And for example, DCA less than 3. I think if you consider this is the effect that you want to study for the secondary contributions. Secondary track contribution for the DCA between is more or less flat, or maybe even more towards the high DCA. So, example like DCA less than 3, you change to less than 2, that's probably at least like 1/3 amount of the contribution that get removed, or plus, that's depending on the distribution. I think this is, to me, I feel it's a reasonable kind of change. You want to, but you couple that, you don't want to have large impact on other parts because we also primary tracks, the DCA has our cut has a finite efficiency. If you want to put too tight cut, the efficiency may come in. That's as the effect we check. If you change to a too tight value, the cut you study is not only one systematic effect, then that becomes complicated. You might want to isolate them to check that. So when you have a multiple contributions there, you may sometimes want to consider correlations where you cut various different cuts. I see that particularly like in the V0 particle reconstruction, you probably have a list of all these topological variables. And you want to vary one by one to check the systematic. That is okay approach. But many of these are absorbed. They may kind of be correlated with each other strongly. So in that sense, you may want to think about just to vary them, scan the full phase space. Say if you have 5 variables, you may want to scan 5-dimensional space to check the variation. That will take into account the correlations here to see the impact in your results. So the cut variation, so maybe this is just an example. I think similarly, you want to also like to check the N keys or others. We can discuss in details later on how we want to think about how much you want to vary to study the effects. So the next category is regarding choose different method to evaluate systematics. This is also a standard or common exercise when we do that. Like if you have a raw signal, this is a 5 meson reconstruction through the K plus K minus channel. So you do a signal extraction. You have many ways, or not many ways, several ways to do that. Right? You choose a different signal function form, and because 5 meson, this is not exactly quite regular, probably convoluted with your detector resolution. And for the background function form also is a little complicated, or it's, at least it's not a very exact as unknown part, whether it's a linear, second order polynomial, or exponential. You also want to choose, when you do the fit to do the extraction, you also want to check different fit ranges. And also the fit may not describe the signal very precisely. You can see there's some probably slightly offset in terms of description, and you may want to compare fitting versus counting, etc. Another example, I like to do the PT extrapolations, and this is a recent Hypertriton paper. You measure the yield in the finite PT region. You extract the low momentum to get a total d in dy. You have several different choices, right, to do extrapolation. So how those are the typical different methods to do that. So how do you combine this? This is you have several choices. I call it discrete cases. And this is, I think, is probably more not a general guidance you can think about how to compare. In the case if you have two variations, and if you have one is preferred over the other one, typically you quote the one the central value. The difference is your uncertainty, one sigma deviation. And if these two are equal variations, you don't have to know which one's right or better than the other one, you quote the mean value, right, the average of the two, and the uncertainties, this is as an unbiased estimator. I think I recently found that most people probably divide this by 2, which may not be a best way to estimate. As an unbiased parameter, this is supposed to be a square root of 2 over square root of 2 factor, which we can discuss later. In that case, this is our typical consider as a Gaussian shape like 1 sigma deviation. If you consider your variations two extreme cases, so you cover the, say, boundaries of your variation. That's this, I think, probably infamous or famous square root of 12 factor to convert this into a 1 sigma standard deviation. But you have to justify actually your variation are the two extreme cases. And those are certainly all case by case in the design. If you have n variations and the standard procedure, you average values are central value. The standard deviation, I think, do a small correction to do as an unbiased estimator. That will be a best estimation to do called as for these discrete cases. I think in the case of this I call the category, you use a calibration or independent measure. Basically, you have uncertainty associated with that, like the TPC tracking efficient uncertainty or the momentum resolution uncertainty. How do you do that? First, you have to assess. I think how do you obtain this uncertainty? That's a typical question that we are asking. What is uncertainty of the TPC tracking efficiency? So we have now a very dedicated task force addresses using an independent measure from data, using say the count of 3' decay to check the uncertainty. You can calculate this efficiency from both data and Monte Carlo. That could validate our embedding and check the efficient uncertainty. That give you what the range of uncertainty come from. The momentum resolution, our embedding done, to give you the best description of the momentum resolution. The exercise, at least being exercise in star so far, I think I see this is probably one of the best exercises trying to use JSI signal and to constrain the momentum resolution. And this is and we tuned our embedding simulation parameters to match the measured data. So this is actually another independent way to check the resolution. So once you have this resolution or efficiency to convert into your systematic, that's rather straightforward. I consider this the so-called you can say continuous parameter variation. So you have a systematic error coming from tracking efficiency or other cases. This you can do a standard propagation using a simple algebra. In some cases, you have implicit continuous parameter, like what is a momentum resolution impact into, say, your the the correlation function. Like, what is the energy loss uncertainty correction on your spectrum? There's no direct kind of analytical function or algebra to do that. You can do this in the Monte Carlo way. Basically, you vary your parameters by +1 sigma and check the numerical results considered as uncertainty impact on your results. The question also, when you have involve multiple parameters, you may need to consider variance. Actually, this is probably a challenging part, because that question is also how do you derive this covariance between parameters? But maybe this is a little bit rare cases. We can discuss later. So when we do this, all these variations of count variations or check different cases, when you evaluate the systematic uncertainties, they always come with, you compare results, they always come with also statistical fluctuations. And so in STAR now there's a very, I would say also common or widely used procedure to try to remove this statistical fluctuation in your systematic error evaluations. This has been pioneered by several papers, and now I think it's rather standardized. The question is whether when you evaluate, vary a cut, you calculate your final results and compare with your default results, the difference, they could incorporate some statistical fluctuation. Because typically this comes from the cut variation, the samples are nearly fully correlated. So you should subtract the statistical fluctuation uncertainty, and the statistical fluctuation is calculated based on the result statistical error bars. And then in the case, if your variation is smaller than statistical error bar, you consider there's no contribution from this source. And if there is finite contribution, you remove that. So this actually works reasonably well if you have multiple systematic sources, eventually add them together. And the total contribution is, I think, a reasonable estimate. The question also here is, in some cases, you may end up with, you only have one probably source that passes your biotech, or even no one, nothing passes. So the question is, what do you quote for your systematic errors? And we can discuss later on, but please think about it, and we can discuss in maybe lunchtime or coffee break. So, the ballot, this is called ballot check. I would recommend now everyone want to do the similar exercise in your analysis. And when combined all the uncertainties from different sources, generally consider they are all rather independent, and you just add them in quadrature to obtain your systematic errors. Common exercise, unless you have a compelling region that some sources are their correlations or their covariance. Yeah, but there's also standard procedure you can combine them. A few cases I would say I want to point out is you probably heard this. So when you do the ratio measurement, like IA or particle ratios, the advantage of or the good thing of this in some of the systematic they may get canceled out or at least reduced. The question you want to be careful is what are remaining? You don't want to just do a direct cancellation, do a direct systematic error subtraction. You may end up with no systematic errors or underestimate systematic errors. You want to evaluate basically the covariance also carefully. What are the correlated parts? What are the that can be cancelled out? For instance, the IA calculation. And when we say these two are the yield measurement in the AA versus yield measurement in PP, they are largely cancelled. I think the cancellation in the sense is probably in the single track TPC efficiency part that's largely cancelled out. While even in terms of tracking efficiency, there are some part associated with that. You have to be careful. For instance, there are some dynamic calibrations affect the TPC part, affect TPC. They could affect in the high occupancy AA collisions that don't appear in the PP collisions, the different PID methods, etc. So when talking about cancellation, you want to think about actually, maybe you want to even divide your systematic error further. Which part is cancelled, which part is not cancelled. You have to think about more detail. You shouldn't just okay, I cross out all the efficient uncertainties out. That's probably oversimplifying. Another case is also you combine probability measurement from multiple data sets. That's also nowadays we have 20 years of star data and want to. It's very reasonable that to combine results to get best significance. Certainly, one key thing is you want to check the consistency between the two measurements. If there's a difference beyond statistical error and also beyond the individual systematic errors, you may want to start investigating more and the potential systematic difference. As I mentioned, or similar to before, to the case, this is actually a similar case as you divide a single data set into multiple data sets. But so in this case, you want to fix the first, and inflating is always a last choice if you don't find any reason for that. Combined data sets, the standard technique guided by PDG is doing the weighting based on the statistical error 1 over sigma square, and it's not a new thing. In terms of systematic errors, in STAR, I think generally you can consider the data sets, particularly say the same clearance system from different years. There's probably large correlation between different years. Actually, it's not I don't think it's a very simple task, but I recommend you want to consider certainly very carefully the correlation between these two, between multiple data sets, and what are the common systematics. Once you identify the common systematics, and combine them also, the procedure-wise is also rather straightforward or standardized. So I think I'll finish here. And as I mentioned, I can only give you probably a few recommendations what you want to think about. First of all, for maybe some of you who did already lots of analysis, you know that systematics require lots of effort. But for the new student, new people, try to also consider spend lots of time and check your systematic extensively. The number one is really you want to know your experiment analysis in very great detail and understand each step and the selection cuts. Why you apply this? What systematics could be involved with this cut? I think it's worthwhile to think about through. We have already 20 years, so I think this is probably one thing that get oversimplified. There's already people who did this analysis 5 years ago. You just inherited or whatever you get left and did the same thing as before. That's not the right way to do it. You need to rethink all the previous experience. Particularly now, we have now better detector, large study samples, everything is getting improved. Some of the systematic that get ignored or neglected before, that become important now. So you have to evaluate this very carefully as well and rethink all this previous exercise. And for the choice of the variation, I think it's probably using the common sense. This is also quotation. How do you vary that? And use some reasonable approach for this distributed uncertainties. This is a Barlow check to avoid the common statistical uncertainty. I feel it's rather standardized. I would recommend everybody to think about that and to include in your exercise. And also avoiding either inflating your error bars or oversimplifying your systematic error bars when you combine results. Try to always investigate further and understand the difference. And doing this inflation is always last choice. Thank you. Yeah.
Thank you. I don't want to cut the discussion. It's very important and very useful to everyone. Questions? Okay.
On slide 7, you said, for example, the DCA, you said change it to 1/3 amount of the change. You mean 1/3 of the DCA default value?
That's right. So first you understand what systematic source you want to check. Here I give the example, the DCA cut is trying to reduce your kind of secondary track contamination in the leak into your analysis, right? So compare the DCA, if you consider second track contribution, the DCA contribution is more or less flat, which is a little between. Maybe they are biased towards even high DCA region. Just consider the flat. So 3 versus 2, that's roughly 1/3 of the amount you get reduced. And you can consider reasonable variation. You can maybe push down a little bit further, but the reason I choose here consider 2 is if you push down too low, you might start to kind of get affected by efficiency cut. That's very affected us. Well, nowadays you may push this further because with ITPC our D series is much better already. You can consider to push this down further. That's also to also check. And if this is really a systematic effect, you will show up because you are really checking really the systematic deviation from your default value. So that shouldn't, when you do this change and you remove your statistical function out of this, all your different variation, that should come up with more or less general consistent results. Right.
Thank you for a good talk. So I've read actually Roger Barlow's articles. It was very good, and I would like to emphasize that there is a YouTube video on previous Juniors Day given by Roger Barlow for this topic. This is very good for everybody. But my question is from this article, more or less, on your opinion. So can you go to the last slide, to the pre-last slide, please? Pre-last. Yeah, this one.
Okay.
So one can come up with many variable systematics and inflate the systematic up to infinity, almost 100%. So what is your case on where to stop? And because the big systematics are also not good for the articles and papers.
Can you repeat what your first part of the sentence?
Yeah.
I didn't catch that.
Until when should a person stop in including all systematic effects? Because one can go up to 100% or infinite and so on.
Yeah. That's a very good question. Actually, that's probably one specific thing is where I can point out is probably this example. Actually, you can consider is okay. Those are I show is just like a few exercise tried, as you said. You can try infinite amount of models coming out. Here,
I mean systematic sources, not within one variation.
Yeah, this is systematic sources. Okay, I'll address two separate. I'll say a few things on this, and I'll talk about the systematic sources. So this one, certainly, there's a couple of required conditions. One, the guidance is you would have probably want to with some this PT distribution with some basic physics kind of input. It's not any function that can describe the data point and shoot up with the one constraint. Certainly, the dNdy should go to 0. A cross section could go 0 at the 0 PT, and another constraint is based on data points that should have roughly equal description in their measurements. That's some guidance you can think about to at least constrain how far you want to vary. In terms of different sources, that's actually a good point. That's exactly I think want to review your analysis steps. I guess you have many sources exactly, and you want to think about to really step by step what really comes in, and like every cut you put in, you may want to think actually any systematic that associated with that cut. Once that's get kind of you do quick evaluation, say this is much smaller, almost negligible compared to others, certainly want to drop it. You don't need to kind of spend lots of efforts to investigate the systematics with very negligible or very small contribution. For the systematics, eventually you want to focus on probably 3-4 very leading systematics, largest contribution that give you the best, the largest that dominant order estimate of systematic errors, right? So that's a very good question. Yeah.
Can I have a few more?
Thank you for the next talk. I want to ask, in case, that we cannot change one variables due to various reasons, then how should we evaluate the systematic from that variable?
When we compare what?
In case that we cannot modify one variables. Modify. For example, like the magnetic fields. It's a fixed value, but we have some systematic from that value.
Good question. That's very practical for now-star analysis. Yeah, that's actually, in some sense, that's something you want to bring up. And as a collaboration, we need to think about that. That's we actually have a data set now to address that. But given the data set you have now, right, that's probably one to care about. What's systematic you want to assess? I would recommend, I think, because those are really unknowns. We don't know actually say the TPC alignment to put precision that it really is. I would suggest maybe you want to do some quick simulation study to investigate the impact. Although I don't have a clear procedure on how to really do that. That's why I think I can think about is basically our TPC calibration, because of the magnetic field kind of constraint that is fixed to one setting. You might think about what the tolerance there, say the alignment, what tolerance that can vary, that can have impact on our momentum distortion. You give a reasonable either estimate or guess and check the impact on your final results. This, I feel it probably can be done, but I'm not sure whether it's easy or not. But that can give you an estimate on the impact and results. Then you can decide whether it's becomes sizable, then you need to probably think about more, or it's negligible, then probably it's not a big effect in your reason. There's other ways you can check actually for this in terms of distortion. I think that's being exercised, but I'm not sure whether has been fully studied. The reason this alignment issue was brought up is because we're looking at the H minus of H, famous H minus of H plus ratio. You compare different regions in the symmetric system. We compare plus and negative eta regions. And this actually a good measure actually in the data to tell you how large the distortion would be. You can fold that into analysis really to estimate impact in the results. That's another way you can right. So yeah.
Thanks. I think John first.
Hi, Xin. I have a question about slide 9. So I would like to ask, like, why do we want to quote the mean value of the two variation?
The two variation?
The mean value of the two variation as our default value, because to my understanding, normally when we calculate the default value, we use the most loosest tolerable cuts. Then we vary it to one end, and we consider that to be the capture or whatever, and then
it depends on you whether you consider these two variations is you prefer one over the other. Right. If you consider these two are equal footing, and I would say just calculate certainly that's average one is probably best estimate. If you have one preferred variation, just quote one as a central value. I said R1 is just preferred one.
Okay.
But in this case, you make sure that certainly you want to, the range of the variation from the other one to this one, the difference should, generally you want to consider at least a good 1 sigma deviation. You don't want to simplify it too much.
Xin, very nice talk. I have one question. Coming back to the Barlow test when you said that, what if we will not converge or there's no systematics? So what is your opinion on that?
I have, my opinion is, in the end, the physics results come out from a measurement, it's probably total systematics. If neither of this coming from the past Barlow check, so which means the statistical are dominant. So in the end, I don't think it's going to be too difficult. You just no contribution, that's okay, or it's very small contribution to the systematic. So the total uncertainty is safe. You can, I think in this case, you can produce results as a total uncertainty. It's okay. If you insist to still separate the systematic out, okay, I don't have a good opinion for that, but we can discuss that. You may consider other way. But I think that it's probably that internal presentation, if you really want to present the systematic, that's a question. But the total systematic, I guess, total uncertainty from the measurement, I think it's reasonable to say.
Thank you.
Thank you. Any questions on Zoom? Okay, a lot of very good discussions, and I agree with Xin that please rethink the previous exercise and do this systematics. So our next speaker is Kong. Discuss about how to give a presentation with